Yo, what's up, guys? I'm going to show you how to do this very important part of calculus. We've been doing first principles up until this point when you first start learning calculus, and if you've done some first principle questions, you'll realize that differentiating is a pain in the ass, right? Because there's a lot of algebra to do. So the reason why this is really important is because instead of having to differentiate like x squared or like square root x or any different combination of x, what if we just say, okay, x to the power of anything, x to the power of n. It's not any particular number that we have. Let's just say it could be any number, right? And then maybe we can find a form where there'll be some sort of pattern and we know how to differentiate really quickly. Okay, this is how formulas kind of get made. Okay, where we just make a really general letter like n, okay, and say it could be anything. Okay, so let's try to differentiate x to the power of n using first principles and see what we get. Okay, now we have dy on dx is equal to limit h approaches 0. So x plus h to the power of n minus x to the power of n on h. Okay, so again, we have a very similar situation where it's really hard to differentiate this guy because there's nothing really to simplify. And we can't really sub h in because we have a 0, like we have h on the denominator, right? And we don't want 0 on the denominator. So we're going to have to do some work with this numerator. Okay, now the difficulty here is if n was any number that we knew, like if it was squared or cubed, we could do some factorizing and expanding. It would be a lot of algebra, but we could eventually do it. Now the challenge of this one is that it could be anything. We don't really know what n is. Okay, now to do this, I'm actually going to show you something here on the side. This is very similar to another question that we did earlier, where if you think about difference of two squares, it's a minus b, a plus b, right? What about a cubed minus b cubed? If it was difference of cubes. Again, if you don't know all these, then it's probably going to be given to you in the exam anyway, but if you're going to get a somewhat of a good mark, you should kind of know at least the square and the cube one. Okay, so these two you should know by now. What I want to kind of extend the knowledge to is what if we had this and we continued down the line. Okay, a to the power 4 minus b to the power 4. Now, this is like a difference of two squares, again, right? It's like a squared minus b squared and a squared plus b squared, right? It's a difference of two squares. And the first one is actually, the first bracket here is another difference of two squares. Like it's a minus b, and then a plus b, and then the back, we can't really do anything to it. And then we get this. Okay, now just bear with me, and I'm going to leave the first bracket a minus b, and I'm just going to expand the second one. Okay, and you'll see why in just a second. But we have this expanding, and we're very capable of expanding these sort of things, right? So it's like a binomial, so we have a cubed plus a b squared plus a squared b plus b cubed. Right? Now, if I just rearrange this slightly, this is what we get. Okay, so why did I just do that? Because if you look at what I'm doing, we have this pattern of a plus b and some other bracket, right? And then if we factorize cubed as well, we have a a minus b, and then some other bracket. So I wanted to know, if we extend it to power 4, and we have a minus b in the first bracket, what does the second bracket look like? Do we have a pattern? Okay, so since this is a recording, okay, you can just pause it if you want to see this, but I'm just going to rub this bit out. Okay, and just bring this guy back up. Whoop. Back up here. Okay. Okay, so do you see any pattern in the second bracket? Yeah, so if you look at the A's, looks like the A's are going up in power, right? It's like A power of 1, A power of 2, A power of 3, right? And if you look like sideways, it goes from A squared to A power of 1 and then A power of 0. Like there's no A's on here. And the B's, it starts from B to the power of 0, B to the power of 1, and then B to the power of 2. And then the B's go ascending while the A's go descending. Same story in our fourth bracket. In our power 4. Starting from A cubed, we just continually, the A's go down, and then at the same time, the B's continually go up, right? So knowing this, is there a way to write a factorization for this guy? Okay, you can see where I'm going because I want to have some formula that I can use for when we have power of n. Okay, so if I was to follow the same pattern, this is what's really good about maths. You identify this pattern, okay, and you know it's going to continue on. So a minus b in the first bracket. The second bracket, we should have a to the power of n minus 1. Okay, you can see if it's power 4, it's power of 3. Like we just keep going down 1 power. I'm going to need to write, whoops, shit. I'm going to need to write this over here. Plus a n minus 2, the a keeps going down, and the b's start to go up. Right? And then we have a n minus 3 b squared. Okay, so a's keep going down and the b's keep going up. Let's just give me a lot more room. Okay, now plus, this is obviously, we don't know how long n is. Okay, so we're going to have to put some ... in the middle. Okay, it's going to go for however long n is. And if we think about the ending pattern, right, the very last number is going to be b to the power of n minus 1. Right? So we start with a to the power of n minus 1, and we also finish with b to the power of n minus 1. And if we just work our way backwards, we're going to have 1a left and b n minus 2. Right? And then that pattern is going to continue on. Okay, so why did we do this? So we did this because now we have a way to write this guy. Okay, so imagine like inside there, that's an a, and then that x is a b. We have a to the power of n minus b to the power of n. Yeah, that's what we have. So if we were to write this over here, right, let's say x plus h and then x power of n. Okay, and we just write this out. We get x plus h minus x. Okay, so over here, we're going to write all this out. Now it's going to seem like it's a lot, okay, but we're going to take our time and just be careful with this. The first one is a to the power of n minus 1. And then we have x plus h to the power of n minus 2. And then we have a b, which is just an x. Okay, I'm going to skip the next one and just jump straight to the ... And then at the end, we have a, which is x plus h. And then we got x, which is b, n minus 2. And at the end, we should just have x, n minus 1. Okay. So, if we simplify the first bracket, we got x plus h minus x. The x's cancel out. Okay, so we just have h, and then we got this whole bracket again. Okay, which is really good news, because if we bring this back to our question, we have a h that we popped out at the top and we've got an h on the bottom. Okay, so this is going to cancel out. So let's just bring our question back. Okay, and this one that we just discovered is this. Okay, so you can see here, if we divide this by h, that's going to be like our question. And over here, if we divide everything by h, these are going to cancel out. Which means dy dx is equal to the limit of h approaches to 0. And we can use some technology and just copy this. Okay, and now we've solved that problem that we have in first principles of getting rid of the h on the denominator. We can now sub h in, so h equals to 0. So we're going to sub, in here we're going to sub 0, we're going to sub 0, we're going to sub 0. And then I want you to notice what's going to happen. Like, if you look at this first one, like if you look at this, if we sub the 0 in, we just get x to the power of n minus 1. If you look at the next one, it's going to be x to the power of n minus 2 times an x. Let's just not write times, let's just write this. Plus dot dot dot. We have x and then multiplied x to the power of n minus 2 plus x to the power of n minus 1. Xn minus 1. Now if you multiply these, if you add the indices, we get xn minus 1. All of these powers are going to be n minus 1. Oh my god, we have a like term. Now the question is, how many of these do we have? How many terms do we have? Because we have that many x to the power of n minus 1s. Well, to really know, let's go, if we kind of come back here, where did this whole thing come from? This came from the second bracket, right? So if you think about, if we have squares, then we have 2 terms in the second bracket. If you have cubes, we have 3 terms. Power of 4, we have 4 terms. So it remains consistent that if we have power of n's, inside here, we should have n terms. We should have n terms. We have n lots of them. And this is the answer. So we now have something nice to use from now on. Instead of having to, that was a really hard question, right? There was a lot of algebra and stuff involved. But once we've proved something in maths, we can just use it forever, okay? Because it's never going to get disproved. So we found this, d over dx on x to the power of n is equal to n x to the power of n minus 1. This is what we proved. Okay, so in the future, from this point on, if you see any question, we can just differentiate like this. Okay, thanks for watching, and I'll catch you guys in the next one.